In the previous lecture, we talked about how to reduce a partial differential equation to two ordinary differential equations by using the method of separation of variables. We now have solving the wave equation. We have three types of wave equations. So heat equations, not wave equations. We have three types. This is the equation of heat equation. This is the general form of heat equation. As partial u by partial t equals alpha squared partial squared u by partial x squared. Alpha, it could be a positive value or it could be like alpha squared. Okay. Here, u of x0 equals f of x for x between 0 and L. Here we have the types of boundary conditions. We have these three types of boundary conditions. The first one is 0 endpoints. As you see here, u of 0t equals 0. And also u of lt is not 0. This is 0 endpoints. And insulated endpoints, we say u sub x of xt equals 0. And u sub x of lt equals 0. Yeah, u sub x for x and 0. And x and t, L and t are both 0. And mixed endpoints, here we have u of x0 is 0, and also u sub x of lt is 0. We have an example about 0 endpoints. If you look at the conditions, you know that it is 0 endpoints. It is, we say u of 0t is 0, and u of lt is not 0. L here is 1. This is L. L is 1. It says solve this heat equation. Partial u by partial t equals 4 partial square root of u by partial x squared. As I said before, lambda alpha squared, it could be a positive value. And here it's 4. That means alpha is 2. We have given the boundary conditions. And also we have given the initial condition. Here, this is f of x. As you see in above, it says the initial condition u of x0 equals f of x. This is f of x. Okay, here f of x is 4 x over 4, and you have given the heat equation. Now we try to solve this heat equation. How to solve? It's a partial differential equation. We must first need to reduce it to two ordinary differential equations. We must reduce it to two ordinary differential equations. As we did before, here we have partial u by partial t equals 4 partial square root of x, so u by partial x squared. This is the heat equation. We first need to reduce this partial differential equation to two ordinary differential equations. How? We say we let u of xt, let u of xt to be x of x times t of t to be a solution for the partial differential equation. We let u to be x of x times t of t to be a solution for the partial differential equation. We now, what we do, we are going to find the partial derivatives that you have in the heat equation. The partial derivatives are partial u by partial t and also partial square root of u by partial x squared. We find these two partial derivatives. The first one is partial u by partial t equals. We take the partial derivative for this function with respect to t. X of x is constant with respect to t. Okay, so we have only t of t. We find the derivative of function of t with respect to t. Since we have only one variable in it, which is t prime, we can say it's t prime. So it's x times t prime. This is partial u by partial t. This is the multiplication of these two functions. In multiplication of two functions, if one of them has only x in it and the other one has only t as a function of t, then the derivative of the function together with respect to t, we just take the derivative for the second. This one is a constant. We deal with this one as a constant. It's a constant times that function. So derivative of t with respect to t is t prime. And the second partial derivative of u with respect to x. We take two derivatives for this function with respect to x. When we take derivative with x, this is a constant. This is a constant. And we have only x of x. We find the derivative of x of x with respect to x twice. You find it is derivative with respect to x twice. We say it is a partial u by partial x squared, partial square root of u by partial x squared equals x double prime times t. We get this one. We solved two examples about this yesterday. This is the partial derivatives of u with respect to t and with respect to x. Now, we put these two into the partial differential equation. Let's name this to be stars. We say put in star. What we get? We replace partial u by partial t by this one. And we replace partial squared of u by partial x squared by this one. And we get xt prime equals, this is xt prime, equals, in the right hand side you have partial squared of u by partial x squared. It is x double prime t. Okay, it's 4x double prime t. 4x double prime t. Okay, now we separate the variables. We put t with t prime, and also we put x with x prime. How? We divide both sides of the equality by 4x t. Here you have this x here. We need to remove this, and we need to remove this 4 with this t in the right hand side. So we must divide both sides by 4xt, and we get, if we divide this side by 4xt, what we get? X and x are cancelled out, and we get t prime over 4t. We get t prime over 4t. In the right hand side, if we divide it by 4xt, t and t are cancelled out. 4 and 4 are cancelled out, and we get only x in the denominator. And in the above, we have only x double prime. We have x double prime of x. We say two functions, and these two functions are equal in only one case, if both are constants. We let both equals to lambda. We let both equals to lambda. Okay, this is a constant. We let lambda to be a constant. We say these two functions, this and that, are equal in only one case, if both are constants. If both are constants. So both are equal to lambda. That means t prime over 4t equals lambda, and x double prime of x equals lambda. From this one, we can say that t prime equals 4 lambda t. Is it? We multiply both sides by 4t, and we get, let me write down there, from this, t prime equals 4 lambda t, and x double prime equals lambda x. Okay, and we move these two to the left hand side of the equations. We get t prime minus 4 lambda t equals 0, and x double prime minus lambda x equals 0. These two are the differential equations. So now we could reduce the partial differential equation to these two ordinary differential equations. One of them is first order and the second is second order. This is second order ordinary differential equation, and this is first order ordinary differential equation. As you see here, you have only one prime. The order is one here, and for the other one is second order. This is the differential equations. It's in the first step. And now we work on those two differential equations. We work on those two differential equations to find the solution of them. But here, before we do that, we must find the boundary conditions. The boundary conditions are given to the partial differential equation. So we must find the boundary condition for the differential equations. We must find the boundary condition for differential equations. Here, when we have, let's write down it, u of 0t equals 0 and u of 1t equals 0. We have given these two boundary conditions. Okay, from these two boundary conditions, we can get the boundary conditions for the differential equations. Here, it's u of xt equals 0. Here, x is 0. If x is 0, this equals to 0. That means x of 0 is 0. From this one, we say x of 0 equals 0. X of 0 equals 0. And from this one, x of 1, we say x of x. Okay, so x here is 1. X of 1 equals to the right hand side, which is 0. These are the boundary conditions for the differential equation. Okay, we have these two boundary conditions. And the differential equations are x double prime minus x lambda x equals 0. And also t prime minus 4 lambda t equals 0. We have these two differential equations. And we have those two boundary conditions. Now we solve these two differential equations. We always start from this one. We start from the one which is second order. We always start from the one which is second order. Here, in heat equation, always start from the one which is second order. Now, we say x double prime minus lambda x equals 0. See, x double prime minus lambda x equals 0. And it says if lambda to be 0, we have three cases for lambda. Lambda, we said it's a constant. We said lambda to be a constant. And we didn't say that it's either bigger than 0 or less than 0. That means we have three different values for lambda. It could be positive, it could be 0, and it could be negative. We say if lambda to be 0. If lambda to be 0. But you should remember that u of xt equals x of x times t of t. And here we must find x of x and t of t. We must find the solution for both ordinary differential equations. We say to find the solution, I mean u of xt, we must find a non-trivial solution. That means it must not be 0. We say if it is u of xt equals 0, this is a trivial solution. We don't need that. We don't need that. We don't need that. We need a non-trivial solution. We need a non-trivial solution. We have three different values for lambda. It could be positive, it could be 0, and it could be negative. First, let's say lambda to be 0. If lambda to be 0, then this differential equation becomes x double prime equals 0, is it? If lambda to be 0, we get that x double prime equals 0, because 0 times x is 0. this x double prime equals 0. How to get x? By taking two integration for both sides with respect to x. Okay, taking two integration for both sides with respect to x. We say the integration for x double prime dx equals the integration for 0 dx. The left hand side becomes x prime because we take one integration. If we take one integration for x double prime, we get x prime equals, let's say this is a, it's a constant. Integration of 0 is a constant. Now we take another integration for this one with respect to x. Integration of x prime with respect to x is x equals the integration of a is a constant. It's ax plus b because it is undefined. I mean, integral. We have no lower and upper limits for the integration. This is x. This is x. We now apply the boundary conditions here. We now apply the boundary conditions for this solution. And here we say x of x equals ax plus b. We apply the boundary conditions. Apply the boundary conditions. Okay. Look, we found the boundary conditions for the differential equations, which are x of 0 is 0 and x of 1 is 0. These are the boundary conditions. Okay, you find the boundary condition for the differential equation from the given boundary condition for the partial differential equations. Here we are given these boundary conditions for the partial differential equation. From these boundaries, we can find the boundaries for the differential equation. Yes. No, not boundary. It's not mean that. Boundary is this condition which is given. Boundary conditions. Here we have two conditions, which are initial condition and boundary condition. We have given both. This one is boundary and this one is initial. Okay. From these boundary conditions, you can get the boundary conditions for the differential equations, and we found them, which are x of 0 is 0 and x of 1 is 0. Now we apply the boundary conditions. X of 0 is 0. That means in this solution, we replace x by 0 and then we equal to 0. If you replace x by 0, little x by 0, what we get? We get a times 0 plus b equals 0. So a times 0 plus b equals 0. We replaced only x by 0. And this is 0. So we get b equals 0. So we get that this constant is 0. And then we apply the second boundary condition. So if b is 0, this differential equation becomes x of x equals a x, because b is 0. We have no b anymore. It's 0. Now we apply the second boundary condition. Apply the boundary condition. X of 1 is 0. That's it. We have x of 1 is 0. If x of 1 to be 0, then we replace x by 1 here. Sorry, by here. We replace x by 1 here and it equal to 0 because b is 0. We say a times 1 equals 0. So a is 0. So we get that a is 0. Now we found the value of both constants in the solution. We found the value of both constants in the solution. So the solution x of x equals what? Equals to ax plus b. If both are 0, we get 0 for a. Okay. So x of x is 0. Do we need to find t or not? Look, we say u of xt equals x of x times t of t. If this is 0, if you multiply by t and t be anything, it's still 0. It's still 0. That means u is 0. And at the beginning, I said we don't need a trivial solution. We need to look for a non-trivial solution. This is a trivial solution. This equals to 0. So u of xt is 0. It's trivial solution. So it's not interested. We need to look for a non-trivial solution. That means u of xt must not be 0. In this case, if lambda to be 0, we get that x is 0. And if x is 0, since u is x times t, u is 0 also. That means it's a trivial solution. We don't take that. We don't take that case. So from now, for solving any heat equation, for lambda to be 0, we say it's not a non-trivial solution. We don't take it. We just write down that. We don't need to solve it like this. Okay? And then, for lambda to be p squared, if lambda to be positive, we have 3 cases for lambda. It's either 0 or positive or negative. We solve it for 0, and we get that. We get a trivial solution for u. We don't take it. And if lambda to be positive, if it's positive, we let lambda to be p squared. P be any value. If it's either negative or positive, when we square it, it becomes positive. That's why we put it to be p squared. Now, x double prime minus lambda x equals 0. This becomes, we replace lambda by p squared. We replace lambda by p squared. So we get x double prime minus p squared x equals 0. This is a second order ordinary differential equation. For solving a second order ordinary differential equation, it's homogeneous. It's a homogeneous second order differential equation. For solving homogeneous second order differential equation, the first step, we must need to find the characteristic equation. The characteristic equation. So the characteristic equation is m squared minus p squared equals 0. Here we find the values. We find the values of m. And from this, we get that m is minus plus p. We have 2 different values for m, m1 and m2. Let m1 to be p and m2 to be negative. Okay? Now, we say if we have 2 different values for m, the form of the solution is a e to the power m1x plus b e to the power m2x. Okay? This is the form of the solution. We just plug in m1 and m2 there. m1 is p and m2 is negative p. And then the solution is, so x of x is a e to the power m1x is px plus b e to the power negative px. And you have given that, the conditions, and now we apply the boundary conditions. The boundary conditions are x of 0 is 0 and x of 1 is 0. Apply. After finding the solution, we need to find the values of constants. I mean a and b. In the first case, we will lambda to be 0. We get 0 for both. Let's see for here. Apply the boundary condition. X of 0 is 0. We have 2 boundary conditions. X of 0 is 0 and also x of 1 is 0. We apply this boundary condition. We replace each x by 0 and we equal it to 0. This is x. In equation of x, we replace each x by 0 and we equal it to 0. If you replace each x by 0, we get a e to the power 0, because p times 0 is 0, plus b e to the power 0 equals 0. And so we get that a plus b equals 0. This is for the first boundary condition. And for the second boundary condition, apply the second boundary condition. Let me do it here. Apply the boundary condition. X of 1 is 0. If x of 1 to be 0, here, in this solution, we replace x by 1 and we equal it to 0. And we equal it to 0. We say it is a e to the power p plus b e to the power minus b equals 0. We now have these two equations, this and this one. From these two equations, we can solve them to find the values of a and b by either substitution or elimination. We get that a is 0 and b is 0 in this case also. I leave this for your service, okay? Here, solving, let's say it's equation 1 and this equation 2. Solving equation 1 and equation 2. You can use grammar rule, you'll get that a is 0 and b is 0. We get that a is 0 and b is 0 also. A is 0 and b is 0. If both are 0, so x of x is a times e to the power px plus b times e to the power negative x, negative px. So if a and b be 0, we get x of x equals 0. And so u of xt, which equals to x of x times t of t, it equals to 0. So u of xt equals 0. It's not interesting. It's a trivial solution. So it's not interesting. Okay, it is not interesting because this is a trivial solution. Here, in the case if the first one, the first solution is 0. I mean the first ordinary differential, the solution for the first ordinary differential equation is 0. We don't need to find the second, the solution for the second one, because the multiplication is still 0. And it's not accepted, it's not interested because it's a trivial solution. We need to find a non-trivial solution. So in case lambda to be a positive value or lambda to be p squared, we get a trivial solution. We don't get it. We don't take it. Okay? From now, if you see any heat equation, you can just write down by, you know, a line, in a line, you can write down, since u of x t equals 0, we say for lambda, you can say for lambda to be 0 or lambda to be p squared to be greater than 0. We get that u of xt is 0, which is a trivial solution and it's not interesting. You just need to write down that. سيرك أبي أشتري هالبنوس يعني توناك نمس مونيا إيش تا زان فلام لما دوك هاو كل شيء دي كل شيء هذا بردستان بيز ناك عمي بوك بيز ناك عمي بوك أنا مش solution يحسب بيقدر بينس أوكي بيقدر أزان بروفني بيز ناك يعني بروفني مش شكال كاتي أوبد ورينا أنت شيكال هل يكسر characteristic يعني كدو زيرو كجيش تام كيسانا for lambda to be 0 and lambda to be bigger than 0 that's not interesting because we get a trivial solution, that's all. Okay, and we just work for lambda to be a negative value. If lambda to be a negative value, we say lambda to be less than 0. We let lambda to be minus p squared. Yeah, lambda is always negative if equals to minus p squared, because p squared is always positive, and if you give a negative sign to it, it's always negative. Now we find the solution for x, and then we find the solution for t. Okay, as you see in the previous two steps, in the previous two cases, we didn't work on t because x is 0, so you don't need to work on t because u becomes 0. Okay, but if x is not 0, then we work on t. We work on t and find its solution. Yeah, x double prime minus lambda x equals 0. So if lambda to be minus p squared, if you replace lambda by minus p squared, we get x double prime plus p squared x equals 0. We just replace lambda by negative p squared. Negative times negative is positive, and you get p squared. That's it. This is a homogeneous second order differential equation. This is a homogeneous second order differential equation. To solve a homogeneous second order differential equation, what we do, we need to find the characteristic equation. We need to find the characteristic equation, and we just find the homogeneous solution, which will be the general solution. Here, the characteristic equation is m squared plus p squared equals 0. And here we can say that m equals plus minus ip. We get a complex value for it. We get a complex value for it. And the real part is 0. The real part is 0. We said if we get complex values for m1 and m2, what's the form of the solution? The form of the solution is e to the power. We say if the solution, if m1 and m2 to be alpha plus minus I beta, we say the solution is e to the power alpha x times a cosine a cosine beta x plus b sine beta x. Okay, plus b sine beta x. Here we found alpha and beta. What's alpha here? Alpha here is 0, and beta is p. Alpha is 0 and beta is p. We just replace alpha and beta in that row. That's the solution. We say x of x equals e to the power alpha x. What's alpha? Alpha is 0. E to the power 0 times a cosine beta is p, px plus b sine beta is px, and x of x is e to the power 0 is 1, and we get a cosine px plus b sine px. This is the solution. This is the solution for the ordinary differential equation. Now we apply the conditions. The same as we did. It's repeating the steps. We do the same step in all cases. Now we apply the boundary conditions. The boundary conditions are x of 0 is 0 and x of 1 is 0. We say apply the boundary condition x of 0 to be 0. And we get that if we replace x to be 0 here, what we get? If we replace x to be 0, sine 0 is 0. So the second term becomes 0. And in the first term, we get, let me write down, a cosine 0 plus b sine 0 equals 0. This is 0 and this is 1. So you get that a is 0. So a is 0. We now replace a by 0 in the solution. That means x of x equals, if a to be 0, so this theorem becomes 0. And we get that b sine px. B sine px. Because a is 0. Now we apply the second boundary condition. We say x of 1 is 0. If x1 to be 0, we replace each x by 1 and equal to 0. We get b sine p equals 0. Sine of which angle is 0? Sine of n pi is 0. Sine of n pi is 0. So if p to be n pi, we get 0. Sine of n pi, we say if the angle is at this or that, its sine is 0. So this pi, 2 pi, 3 pi, 4 pi, 5 pi, and in the clockwise direction, negative pi, negative 2 pi, negative 3 pi. Look, here we have n pi. We say p equals n pi. So if p to be n pi, we get 0. We don't equal b to 0 because it's a constant. Okay, if it's 0, we don't get any solution. That's why we equal p to be 0. We equal p to be 0. And in this case, we say p is n pi. If p to be n pi, so the solution becomes, we let b to be 1. We let b to be 1. It's a constant. And it's not equal to 0. We let b to be 1. For easy to get the solution here. X of x equals b sine px. We replace b by 1 and p by n pi. We get x of x equals sine n pi x. This is the solution for x. After finding a non-zero solution for x, then we work on t. After doing this, then we work on t. Now let's work on t. Let me see. Okay. To work on t, we say t prime minus 4 lambda t equals 0. This equals 0. But lambda is p squared, is it? It's negative p squared, sorry. It is t prime plus 4 p squared t equals 0. But we found p. P is n pi. P is n pi. We replace pi n pi. And we get 4n squared pi squared. And here we get t prime plus 4n squared pi squared. If you replace p by n pi, so p squared is n squared pi squared. T equals 0. Then from this, it is first order. It's separable method. You can apply separable method to find the solution. We put this term to the right hand side first. We put t with t prime and other terms together. We get t prime equals minus 4 n squared pi squared t. And we divide both sides by capital T. And we get t prime over t equals minus 4 n squared pi squared. That's all. Now, to find t, it's t prime over t. It is t prime over t. We take integration for both sides with respect to t. And here we take the integration for both sides. Integration for the left hand side is ln t. It's ln t. And integration for the right hand side is -4 n squared pi squared t, because we take the integration with respect to t. Okay. Now, how about t? How to get t? We have ln t. How to get t? We take e for both sides. We take exponential for both sides to get t. It's ln. How to remove this ln here? We must take e for both sides. We get t equals e to the power -4 n squared pi squared t. This is, sorry, it's plus c1. It's plus c1. So t is, if we take ln for both sides, after taking the integration, we get a constant of the integration, which is c1. We take e for both sides, so t is e to the power c1 plus, so it's c1 minus 4 n squared pi squared t, and so t equals e to the power c1 times e to the power -4 n squared pi squared t. And here t is, we let this is a constant, we let it to be b e to the power -4 n squared pi squared t. This is t. So now we have x and t. The multiplication of them, which is not zero, is a non-trivial solution for u. It's a non-trivial, so the solutions are x of x is sine n pi x, sine n pi x, and t of t is b e to the power -4 n squared pi squared t. These are the solutions for both differential equations. And you see u is the multiplication of them, and u of xt is b sine n pi x times e to the power -4 n squared pi squared t. And this is the solution of u. It's non-trivial. This is a non-trivial solution, so it's accepted. Now we work on this one to find the value of b. We must find the value of b. How? We can get it from the initial condition. This is the initial condition. We have given that u of x0 equals pi over 4. U of x0 equals pi over 4. But in this step, instead, we write down all the cases. We say for lambda to be 0, we get a trivial solution. We write down all the cases. For lambda to be greater than 0, we get the same. We get a trivial solution. And for lambda to be less than 0, we get a non-trivial solution. And the solution is u of xt equals b times sine n pi x times e to the power -4 n squared pi squared t. This is u. Now we apply the initial condition to get the value of b. We must find the value of b. How? We say u of xt equals b sine n pi x e to the power -4 n squared pi squared t, and un of xt equals bn of sine, bn times sine n pi x e to the power -4 n squared pi squared t. Here n equals 1, 2, 3, and so on. It's actually n starts from 0. But if it's 0, we get sine 0 and we get 0 in that case. That's why we don't write down n to be from 0 to infinity. Okay. Now we say un. So what's the sum of all iterations? u1, u2, u3, u4. U of xt is the sum for n to be 1 to infinity for bn sine n pi x times e to the power minus 4 n squared pi squared t. This is a Fourier series, is it? Is the Fourier series? Now we find bn. Look, why did I write down b here for e to the power c1? As e to the power c1, we let e to the power c1 to be b. I didn't say it's to be a. Okay, here we always get a sign for it. That's why I write down it's b. Okay, for sign for it, we just need to find b. We just need to find b. That's all. And here bn equals, what's L in the initial condition is given that this is the initial condition. This is f of x, and this is L. L is 1. It's half range for a series. It's a half range sign for a series. So Bn is 2 over L, the integration from 0 to L times f of x times sine n pi x of L dx. Bn is 2 over L. Yeah, L, we have u of x0 equals x over 4 for x from 0 to 1. Okay, as L is 1 and f of x is 4 over x over 4. This is f of x, and L is 1. This is the initial condition. It's given as 2 over L, integration from 0 to L for f of x times sine n pi x over L dx. So Bn equals 2 over L, which is 2. Integration from 0 to 1, because L is 1, 2 of 1 is still 1. F of x is x over 4 sine n pi x over 1 dx. And this equals to, here we take this 4 to out of the integration, we get 2 over 4, which is 1 over 2. The integration from 0 to 1 for x times sine n pi x over L, which is 1 dx. Now we have multiplication two functions, which is x times sine x. We can use short method of integration by parts to get the result. Here, to get the result of this integration, we take d and I. We put x to be d for the derivative because we get 0 while we take derivatives. And for integration, we have sine n pi x. So the derivative of x is 1, and the derivative is 0. And integration of sine is negative cosine. But we must have the derivative of the angle, which is, yeah, it's negative cosine. It's minus 1 over n pi cosine n pi x. Again, we take another integration. The integration of cosine is sine. It's minus 1 over n squared pi squared sine n pi x. Now we multiply these two minus, we multiply these two. This equals to here Bn is minus x over n pi for cosine n pi x. Here negative times negative is negative. It's positive, sorry. Plus 1 over n squared pi squared sine n pi x. X from 0 to 1. If you replace x by 1, here we get cosine n pi. and here we get 0. Sine n pi is 0. We get Bn equals. This becomes 1 because there's x. If you replace it by 1, you get minus 1 over n pi times cosine n pi plus 0. This is f(x to be) minus. Replace x by 0. If you replace x by 0, here we get 0 because x is 0 times cosine 0 is still 0. And sine 0 is still 0. Okay? This equals to minus 1 over n pi. And cosine n pi is negative 1 to the power n. That's it. Cosine n pi, if it's even, we get 1. And if it's odd, we get negative 1. So it's minus 1 to the power n. This is Bn. Now we replace Bn into that series. So u of xt equals the sum n from 1 to infinity. For Bn was minus 1 to the power n to the over n pi times sine n pi x times e to the power minus 4 n squared pi squared t. This is the solution. This is the solution for that partial differential equation. Okay. So here I forgot to write down this half. Here we have a half, and here we have a half. Here we have a half also. So it's 2. That's 1/2 times negative 1 over n pi times negative 1 to the power n. Here we have 2. Okay. So this is the solution. We now have another example, which is about insulated endpoints. Here, the boundary conditions are insulated endpoints. We use method of separation of variables to solve this. It says use method of separation of variables to solve this heat equation, where these are the boundary conditions. As you see, the boundary conditions are u sub x of 0 and x, which is 0, and u sub x of L and T is 0. Here, these are the insulated endpoints. The initial condition as u of x0 is x. U of x0 is x. Here, we should first write down the differential equations. I mean, we need to reduce this partial differential equation to 2 differential equations. Okay, here I'm just going to write down the differential equations. It's the same as the previous example. Okay, we let u to be x of t, t of t, then we find the partial derivatives, then we replace into the partial differential equation, then we equal it to lambda, and then we get the solutions. We get the differential equations. We say we reduce the partial differential equation to the differential equations x double prime minus alpha minus lambda x equals 0, and t prime minus lambda alpha squared t equals 0. We get these 2 differential equations. I'm not going to do the process. The process is the same as the previous ones that we did. Okay, here instead of 4, you have alpha squared. This is the only changing. Now we solve these differential equations, where we have 3 cases for lambda. So if lambda greater than 0 or lambda to be 0, we get that u of xt is 0, which is a trivial solution. And not interested. Okay. We now have only one more case for lambda, which is negative. So if lambda to be less than 0, and let lambda to be minus p squared. We let lambda to be negative p squared. And from this, what we do, if lambda to be negative p squared, we say x double prime minus, it becomes plus p squared x equals 0. Is it? So this differential equation, if we replace lambda to negative p squared by negative p squared, we get x double prime plus p squared x equals 0. And the solution here, the solution as x of x. It's the same as the previous one. That's why I'm not going to write down this in detail. X of x is a cosine px plus b sine px. This is x of x. Now what we do, we are going to apply the conditions. We have two boundary conditions, which are u sub x of 0t and u sub x of lt. So we first must find u sub x. We must find u sub x. Here, we replace x by 0 in u sub x. Look, you see the boundary conditions are x of 0, sorry, x prime of 0. Look, it is u sub x. It is u sub x means x prime, derivative with respect to x. So we have x of x. If we find its derivative, we get x prime. So x prime of 0 is 0. And x prime of L is still 0. So here we have the boundary conditions for x prime, but here we have x. So from this, we should find x prime. Let's find it. X prime of x equals, the derivative of cosine is negative sine. We get minus a p sine px plus bp cosine px. Derivative of sine is cosine. This is x prime. Now we apply the boundary conditions. X prime of 0 is 0. So here in x prime, we replace each x by 0 and equal to 0. And also we replace each x by L and we equal it to 0. Both to them. Now apply boundary condition. X prime of 0 is 0. That means we replace each x here by 0 and we equal it to 0. If we replace each x by 0, the first term we have sine 0. Sine 0 is 0. So minus AP sine 0 plus BP cosine 0 equals 0. This is 0 and this is 1. Okay, this is 1. And here we get that BP equals 0 and P is not 0 because P is negative. P is not 0. We said that, look, P is a non-zero value. P is a non-zero real value. So from this, B must be 0. P is not 0. B must be 0. And here, it's for the first initial condition. For the second one, look, for the second one, from now, B is 0. That means we delete this part from the from x prime. From x prime, we delete this part, this one, because B is 0. And apply boundary condition, x prime of L is 0. And so we get minus a p sine PL equals 0. A is not 0. A must not be 0, because if it's 0, you don't get any non-trivial solution. And P is a non-zero value. Here, PL must be 0. PL must be, sine PL must be 0. When sine of an angle is 0, if the angle is n pi, we say, if the angle is n pi, then its sine is 0. So from this, say, أم بشام بو بالصفر بولا بري بيك الصفر قال معنى ناقص AP sine PX. أجل X كم L بيت X sine كم بالصفر لجي X L دانم X sine كم بالصفر إيه بشي AP ناقص AP sine PL X sine بالصفر إيش كاتك sine صفر أقول شكمان N pi بيت اللي أقول شكمان شيء PL قاعدة PL بيت شيء بيت N pi بيت. So from this we say PL must be n pi, and so P is n pi of L. This is P. This is P, and we say okay, and here x of x. P is that, sorry, B is 0, P is that, and A is for x prime is that. So P is n pi over L. So x of x, in x of x, this one, this one. This is x of x. In this one, B is 0. B, we found that it is 0, but A is not 0. A is not 0. X of x equals, you replace P by n pi over L. A cosine n pi over L x. And we let A to be 1. So x of x, it's for easy to take the solution. That's why we replaced by 1. A is a constant, could be any value except 0. Okay, and we let it to be 1. It's easy. X of x is cosine n pi over L x. This is the solution for x. Now we should find the solution for t. We say t prime minus, sorry, plus t prime plus, if we replace lambda by negative p squared, plus p squared alpha squared equals 0. But p is n pi over L. P is, and we replace by that. Here we get t prime plus n pi over L. N pi over L t times alpha squared is all squared. T equals 0. So from this, we can say t prime plus n squared pi squared alpha squared over L squared t equals 0. And now here we solve this first order differential equation, and we get that I'm just going to write down the solution, okay? So the solution, we get ln t equals n squared pi squared alpha squared over L squared t. And then we take exponential for both sides. We get t equals, let's say e to the power. As you see here, since x is cosine, that means here we get a cosine for a series. So that means we must have a. That's why I'm write down a for the constant. A to the power n squared pi squared alpha squared over L squared t. This is t. Now we say u of xt equals t of t times x of x, and this equals cosine, a cosine, I forgot to write down a cosine, and pi x of L times e to the power n squared pi squared alpha squared over L squared t. This is u of xt. This is u of xt. But here un of xt is an cosine n pi x over L times e to the power n squared pi squared alpha squared of L squared t. For n to be 0, 1, 2, here we take n to be 0 also. Because in the previous example, if n to be 0, we get 0. That's why we don't take that iteration. But here we must take from 0 to get a naught and a n also. And u of xt equals a naught over 2. This is the rule of Fourier series. A naught over 2 plus the sum of n from 1 to infinity. Look, here we take n to be 0 for here, and the rest from 1 to infinity to the series. Okay. It is an cosine n pi x over L times e to the power n squared pi squared alpha squared over L squared t. And here we must find a naught and n. But here we have given both f of x. This is f of x, which is the initial condition function. The initial condition function is f of x, and L here is still L. It's only L. Yeah, we have given that u of 0x equals x, where x is from L, from 0 to L, and f of x is x, and L is capital L. This is initial condition. It's given in the example. Now you find a naught. A naught is 2 over L times from 0 to L for f of x dx, and this equals to 2 over L integration from 0 to L, from 0 to capital L for x dx, and this equals to 2 over L. Here the integration is x squared over 2 from 0 to L. We replace by L, then by 0. It's L squared, and so the result is L. This is L. I naught is L. And an is 2 over L, the integration from 0 to L for f of x times cosine n pi x over L dx. Here we need to find this. An equals to what? Find it by ourselves. Okay, just find this integration. F of x is x multiplying by cosine n pi x over L. find the integration by parts, you'll get the result. And the input A0 and AN. Let's name this to be star. In equation star, we get the solution for the partial differential equation. That's okay. As you see here, we could solve this in 1 page, while the previous one took 4 pages. Yes. Okay. Here, you can neglect some cases that you know that they don't get the trivial, non-trivial solutions.